So now we are going to expand beyond metrics and actually start covering the various kind of object detectors that we actually see. And we can actually broadly categorize them as actually shown in this picture as kind of a single stage or a two-stage detectors. And there's a kind of a trade-off between the two. The single stage detectors are actually typically simpler and they are more appropriate for target devices such as smartphones and other kind of lower power devices, and they are quite efficient in what they do. However, in terms of performance, they're not really as performant as the two-stage detectors. And so here we are going to be focusing on two-stage detectors, and we are going to be treating the so-called region-based family of object detectors, and that will take us all the way from RCNN, faster CNN, faster RCNN, and this is basically faster RCNN is also the last kind of object detector we're going to see, that it is almost considered today as a bread and butter for object detector. Even in the year 2023, where this video is actually shot, faster RCNN is considered to be a mainstream object detector several years after its original appearance, because it is very performant, it is very intuitive to understand, and also potentially to tune, and has been deployed to real-time systems which are on the mission kind of critical side, like robotics and so on, as well as video surveillance. And I also wanted to mention it that definitely we have advancements on this topic with transformer-based architectures, the visual transformers and so on, and attention-based mechanisms. Many of them, however, do suffer from the latency problem, and that does not allow us to deploy them in real-time systems, at least not yet. So we'll be focusing on RCNN-based approaches or region-based approaches, and try to understand them, and then perhaps at a subsequent iteration of this, we will treat transformer-based or attention-based mechanisms for object detection. We are going to see now the first of the members of this family that is started, if you like, the whole family from that point onwards several years ago, called region RCNN. And the region RCNN can be described in a kind of a straightforward way. Of course, there are some, I will call it algorithmic details that you should not be very familiar with, and I'll refer to those from the website, from the course website, when I'm actually reach this point. But let's assume that I have, let's say, a scene that consists, let's say, of, I don't know, two objects, let's say a table and a person over there. And the first thing that actually happens, and that's why I took actually the name region, is that we need to come up with some region proposals that it will allow subsequent kind of stages to further refine and make up their mind with respect to whether they contain an object or not. But right now, at this first stage, I will call this kind of first stage segmentation. So in this stage is we need some kind of a data structure. We'll call it this data structure a graph. The graph is typically, evidently, and is consists of vertices and edges. And with vertices, we are associated with vertices a pixel. So vertices are pixels, let's say Vi, that belongs to the set of vertices V. And with edges, we represent here as pairs of neighboring pixels. And we do define also dissimilarity or similarity. You can think about it in any way you want. Vi, Vj metric that I'll call here W, some kind of weight I will call it. let me write down as dissimilarity. Between Vi and Vj. Let's assume that I define in this case the dissimilarity as, let's say, the light intensity of difference between Vi and Vj. Okay, so that's one of the potential dissimilarity metrics we can actually have. And during this segmentation kind of stage, we partition. So let me write this down. A segmentation S is the partitioning of V into components such that each of component C that belongs to that segmentation S corresponds to a group of pixels that have high similarity. So it's actually useful now to go to our site over here and actually see a visual example of that. And let's see this kind of a graph-based segmentation section. What is the result of that? So what we just discussed. The ultimately we have an input image. We are forming some form of a graph to represent, if you like, the segmentation problem. And based on that graph and based on that kind of metric that we just discussed, the outcome of this exercise is the set of initial segments that are produced. And as you can see here, even slight light differences between what is definitely one semantic part of an object, let's say the leg of the athlete over here, will result into multiple segments. So we're not really looking here to do anything more intelligent than just looking at similarity or dissimilarity between pixels to be able to get these kind of very rough ideas about an object. And you know, in some instances, even as you can see here in this kind of area, we may actually define a segment as well, and that is have absolutely no semantic information as to what is behind it, just basically based on color. And so after the initial, these kind of regions are produced based on this similarity metric, we will use now an algorithm that it will is actually titled here the hierarchical grouping algorithm, to group these segments, initial segments together. And we form the output of this kind of grouping algorithm, that it is kind of iterative in nature and will start result, it will gradually kind of evolve in getting from a situation where we have plenty of segments and to few segments. And these fewer segments are ultimately going to be limited to 2000. So we are going to be producing 2000 of those regions. Inside this region is basically one of those segments, or more than one segment. But the bottom line is that the algorithm is going to result into these proposals. These are the regions that we propose for further evaluation at a later kind of stage. So you don't necessarily need to, although you're quite welcome to look at the initial publication, which is actually linked over here, to understand its full detail of what is really happening there. Given that those stages that I'm discussing right now are going to be replaced at a later member of this family that we'll be calling it faster RCNN. Then you don't have to spend a lot of time just going through them, just understand the high-level picture of what we're trying to achieve, and focus a little bit more of your attention at a faster RCNN, which is effectively doing exactly the same work quite differently, using a neural network, in fact. So here's the proposals, all these green boxes. A proposal effectively means to the subsequent kind of stage, hey, there is something in there. I do not know if it is an object or a portion of an object, but there must be some kind of an objectness inside that kind of region that I want you to evaluate. And the subsequent kind of stage, what it will actually do is we'll actually use convolutional neural networks to extract features out of every proposal. And you kind of guessed it, we have regions that are transformed into rectangular regions of 227 by 227, let's say, pixels. And the output of this feature extractor, which could be a residual network, as we have seen in the convolutional neural networks, this residual network, or ResNet, is able to produce a vector out of the whole region that represents what it is inside, creates representations of a length 4096 elements. Okay, so this is at the high level. This is basically what the block diagram is what RCNN is actually doing. So proposal is going through the convolutional neural network, and then the 4096 element vector where that comes out of it is fed into a regressor and a classifier. And what is really the regressor and the classifier is doing, you probably have guessed it based on all the previous discussion about metrics. We have to understand whether or not we have the specific class that we are interested in present there. So we, at the time, they were using a method that's called support vector machines, and that is basically the classification that results into kind of K classes. And in terms of regressor, the regression part is responsible for producing the bounding box coordinates for that specific object that we believe that it is present in the inside that kind of proposal or objects. We have another algorithm that it will process this kind of bounding boxes, and it will it's called non-max suppression, and this based on the metric called intersection over union, a metric we have seen also during the metrics discussion, is going to select out of the many bounding boxes that are being produced one, and that will be the predicted bounding box that is going to be the embedded into the y-hat into our prediction. So this is basically at a high level what is happening. The segments to bigger segments to regions, to evaluation of the feature extraction, to classification and regression, and that was the block diagram of the RCNN algorithm. Evidently, we are dealing with RCNN algorithm that it is non-differentiable end-to-end, because we don't have a neural network architecture that it is going to be applied end-to-end. The only neural network that is actually present over here is the feature extractor. So the whole training process is and was very complicated, but worse than that, we had some significant latency. And when I say significant, and completely unusable latency, even for batch processing jobs, even for offline processing jobs, and every frame was being processed by 2,000 convolutional neural networks, and that number itself tells a lot about the perceived latency. The latency we were getting is on the order of many seconds, and we needed few milliseconds. And that's for that kind of reason, this architecture over here was replaced with another architecture that we'll see now, and it is called fast RCNN. Moving on now to the fast RCNN. So in the fast RCNN, we actually see already some improvements that it will actually help us a lot in reducing the latency. So the first improvement that actually we see here is we don't have 2000 CNNs anymore. We have a single CNN, and this has, if you like, an architecture suitable for feature extraction. We are now extracting a feature that it is, from the whole image rather than a single region. So we maintain, if you like, the selective search that we have actually seen in the previous kind of generation, the RCNN, to produce these region proposals. And but now these regions are suggested based on the features extracted from the whole CNN, for the whole image. So we're actually doing this selective search at a feature space, which of course reduces the computation. And then for each of the proposals, what we have here, that we have a region of interest, an ROI, as we call it, pooling layer, that will extract a fixed length feature vector from the feature map. Okay, so we have a feature map. This is now, as we said in convolutional networks, is what is being produced to represent, if you like, this whole image over here. And we are going to suggest proposals in this feature map. And for each of the proposals, we have an ROI pooling layer that it will extract a feature vector from the feature map. Okay, so that's so what is really this kind of pooling layer? What it really is doing? So the ROI pooling layer converts the features inside any region of interest into a small proposal, into a small feature map that would have a very specific spatial extent. It is, for example, 7 by 7, and the max pooling layers are actually present in there. Takes the initial H by W, small letters H by W proposal window, and it is dividing it into a grid. Each of these grids is a grid of 7 by 7 sub windows, and of course it is selecting one feature because it's a max pooling. As we've seen in convolutional networks, it's selecting the maximum feature out of every sub window, and that's basically what is being produced at the output. Okay, so we have effectively from the features of each proposal via the ROI pooling layer, we have this 7 by 7 feature map which is being produced, and this takes the form of a vector which is flattened to create a vector. So each feature vector then it is fed subsequently to the fully connected layers that are going to create the information which is required to feed the regression and the classification branches. Okay, so evidently the softmax is producing a length k posterior probability distribution, and the bound box regressor is producing a 4 times k candidate regression boxes for each of these proposals. Okay, so that's basically the architecture. So we have we have replacement of the so-called classic machine learning methods like support vector machines and regression into fully connected based regression and classifiers respectively, as we also have the replacement of the 2000 convolutional neural networks. We do maintain, though, non-differentiable blocks, like the generation of the proposals. It's non-differentiable, so the training is still somewhat kind of complicated, but definitely it has been improved from what we have seen earlier. Okay, so the second and so the final destination is really the faster RCNN, and this is where we pay quite a lot of attention because that is really the architecture that we will be using for executing some of the tasks and demonstrating object detection. Inside this RPN, there is this kind of concept of anchors, and to understand exactly why we have this concept over there, I think we need to understand how typically what we call multi-stage detection, sorry, not multi-stage, but multi-scale detection, is done. Okay, so multi-scale detection is going to be done now for using typically three methods. The first, actually I will call it the sort of pyramid of images. So in this kind of option, this is the pyramid of images. And before we go into this kind of discussion of these options, what we are trying to achieve with the so-called multi-scale detection is evidently we would like to have exactly the same level of detection as we have performance if we have small objects or larger kind of objects. And for example, Coco is also notoriously known to contain many objects which are kind of small in scale, which are more difficult, of course, to detect than larger kind of objects that occupy a much larger portion of the image, if you like. And so what we need to do here is to allow to train the object detector to be able to accommodate objects of various scales. So if you can imagine you kind of trying to approach the camera, and maybe I can sort of use my hand now to demonstrate this. So if I'm approaching my hand, then my hand is actually becoming larger and larger. So we'd like to maintain exactly the same performance for no matter what the scale of the object is. So in this kind of first approach, this kind of pyramid of images, we have let's say an image that it is sort of W by H pixels, and we are forming and we are working with this 3 by 3 spatial dimensionality of convolutional filters in that kind of image, but at the same time we would like to work with images which are half of the size of the original image, still maintaining, if you like, the same 3 by 3 filter over there in terms of spatial extent. So we are effectively growing the receptive field of this convolutional filter as related to the size of the image. So we are forming a pyramid of images. So images of h by w, h over 2 by w over 2, h over 4 by w over 4, and so on. And so we are effectively trying to create input data for all sorts of scales by adjusting the image size itself. Now the second option, we are forming the so-called pyramid of filters. And this pyramid of filters option, we are kind of forming an equivalent situation. In this case, we are not adjusting the images, but what we do adjust is we adjust the size of the convolutional filters that we have. For example, this is a 3 by 3, this is a 9 by 9, and so on. So it is equivalent to that. And of course, there are some publications that prefer this option 2 compared to option 1 in terms of ability to accommodate multi-scale detection, but it's kind of beyond the scope to see all these kind of details. The approach that faster SNN kind of adopted is the so-called pyramid This is the so-called option 3, and this is the pyramid of anchors. Pyramid of anchors. Sometimes these anchors are called priors. And what are those anchors and what do they do? So I will draw now a larger kind of picture, an image of, let's say, W by height by H pixels. And I'm going to form anchors and this is basically the center of, I'm going to, the center of a number of anchors, which are effectively windows or regions, if I call it like this, rectangular regions. They have the so-called anchor boxes that are multiple scales. They have multiple scales and aspect ratios. So, you know, they will have each one of them is going to have a certain scale and aspect ratio, and we have multiple of those. Let me draw some more. Maybe this one. Maybe, you know, this one. Different scale. So these are examples of. So the thing that actually happens here is that the filter, as we have seen earlier in option 2, it was varying, but now the filter and the image is kept constant throughout the pyramid. And we have, and we define k anchor boxes, anchor boxes. Of various scales and aspect ratios. Let's assume that we have, let's say, 3 scales and 3 aspect ratios. Then we have, let's say, 9 anchor boxes. We now define a sliding window. This pixel over here is the center of this kind of sliding window. For each of these locations, we produce a vector of features. So we define also window that for each location we produce a vector of features. And effectively, what we actually have here, this kind of feature vector, is going to be an extension. I mean, we're going to be created from a convolutional network, which is an extension to the main network. So if I go back to this picture over here, so we have, let's say, the CNN, and which is the main network over here, and we are going actually to add layers. We will be sharing some of the layers of this CNN and adding some more layers on top of them in order to form the so-called region proposal network. So the region proposal network is not a completely decoupled branch from the main branch, if you like, but is sharing some portion of those layers with the main CNN. If I may draw now the sort of picture over here towards the bottom, I have the sort of backbone CNN that receives this input image X, and it has a number of layers. Some of them are going to be shared between the RPN and the backbone in terms of feature feature maps that they produce. And at the output of this, we have the production of a feature vector. And then this feature vector is fed to classifiers and to regressors that are producing for each of the anchors the following decisions. We have K classification results and 4K, because 4 are the number of coordinates of each bounding box regression results. And for this, we'll have the RPN, effectively this network that you actually see here, is responsible for generating the following output. So answer the question, is there an object in the JF anchor? And the regressor to produce coordinates for each of the K anchors. Okay, so this is the high-level picture. Of course, there are many details. Many of these details are contained in the original kind of paper, which I have over here, and I invite you also to get a printout or get it from the internet and go over some of the, as a kind of primarily reading exercise to see exactly how all these details are coming together. However, I'm going to provide some more detail as to what is happening with respect to training now, but at the high-level picture, I hope everyone is comfortable in understanding what is happening. So we are implementing the so-called pyramid of anchors that corresponds of 9, let's say, anchors boxes for each of the locations that we visit in this kind of sliding window scheme. And for each of these locations, we are generating a feature vector, sharing some of the layers of the backbone CNN. And so the main backbone and the RPN network are not independent. And this, of course, has some kind of spillover effects on the training kind of approach. And for each of these feature vectors, we define whether or not we have, for these specific reference boxes, an object which is being created, which is contained in there, and if there is an object, then we also produce the corresponding coordinates for that specific anchor that we believe that it contains the object. Okay, so that is basically the high-level kind of view. And now what we need to see now, let's look at an example on how we are going to basically train the RPN. Evidently, we need to have a training kind of data set that it is very specific to proposals to answer this type of questions, whether or not, let's say, we have an object in the JF anchor, because the original data set has only bounding boxes for the object. Here we need information for on the anchor level. So we need to go from a data set that has ground truth information at the object level to ground truth information at the anchor level. Okay, so this is what I'm going to draw next. I'm going to draw here a picture, another image over here that will contain, let's say, a person over here. And evidently at the kind of COCO dataset, if I might call like this level, we have a bounding box, the ground truth. And let's say for this specific location we are visiting in, we may have, maybe I draw it somewhere a little bit on the left on that. I may have an anchor like this. I may have an anchor like this. An anchor like this. And let's draw also another anchor like this. These are all the anchors that I have sort of defined in what I call earlier as 3x3, 3 scales and 3 aspect ratios. So given the values, the IOU thresholds, let's say 0.5 and 0.3, values and notation here is kind of familiar from the earlier discussion on metrics. For each of the anchors, what we go and what we do is we use this kind of thresholds to classify these anchors as positive or negative, and to annotate, I should say, the anchors as positive or negative or negative. So for any anchor whose intersection of a union with the ground truth bounding box is greater than TP, then this is going to be a positive anchor. And an anchor for an IOU less than Tn is going to be a negative anchor. And anchors which lie in between, let's say Tn less than or equal to IOU less than or equal to Tp, these are going to be called neutral. So this is how we are actually taking a data set which is originally specified at the object kind of level, and we convert it into a data set which is at the anchor level. During training, we'll be using positive and negative only. We'll be ignoring the so-called neutral kind of anchors, and then we will need to define now our kind of a loss function, which is now a composition of the loss function that is associated with classification and regression. And typically what we have here is we have this type of losses. So we have, let's say, y comma y hat. This is going to be associated with some kind of a form of a summation of the cross entropy associated with the anchor I. These yi's are the ones that we obtain at the anchor level, the labels we obtain with this IOU overlapping method just now, and y hat are going to be the predictions of the classifier that we have drawn earlier for each anchor, and this is going to be your in fact, I think I called the anchors earlier with a small letter k, so let me just change this to maintain kind of consistency. All right, and then this is going to be some summation where we add to the classification result some other summation which is associated with the regression, and the regression is a loss which is called the Huber loss for regression. And over here we multiply with the ground truth label, which is either 1 or 0, to allow only positive anchors to be penalizing the total loss. Otherwise, it doesn't really make any sense to penalize the total loss for anchors which are negative. Therefore, we don't have any kind of bounding box. So let me write this down. Only positive anchors are penalizing the regression loss. Of course, also in terms of indexing, we also recognize that if we do the training on with typically mini batches, we have more than one of those frames, and therefore the associated indices will be at a sort of anchor mini batch kind of level, but that's kind of a minor kind of detail. But let me also write down what this y hat k over there represents is the probability that anchor contains an object. Okay, so this is basically the, and what is really this Huber loss? Earlier we have seen mean square error. We also have the mean absolute error, which is the function, the absolute value function. Remember that in the regression case, we have seen the need to make all the differences between predictions and ground truths positive. And one way of doing it with the squaring operation, and that was basically gives rise to the mean square error. Over here, we can also take the absolute value, and this gives rise to the mean absolute error. But the mean absolute error over here has some form of difficulty to calculate derivatives at this point. So what we do is we smooth this, and we call this the so-called Huber loss. This is the Huber loss, the shape of the Huber loss function. And this is basically it. We are going to be training the RPN, and we are going to then be able to suggest objectness at the anchor kind of level. And then we are going to suggest this as proposals. Those who exceed a certain confidence threshold, we are going to propose it to the main network for the main path, the main branch, if you like, to do what we've been doing in fast RCNN, to classify now these proposals as to and make the final determination both at the classification stage as well also the regression stage, giving us back the desired coordinates.